In 1856, in a laboratory in Leipzig, two men discharged a glass jar full of electricity and wrote down a number. There was no lamp in that room, no beam, no mirror, nothing to do with light at all. They had measured how hard charges push each other apart and how hard currents pull each other together and taken the ratio. The number was about 311,000 kilometers per second. They were holding the speed of light in a notebook, obtained without a single ray of it, and neither man looked twice. But here is what they left out of every explanation of this you were ever given. That number was never a fact about light. It sits in the energy of a stone, doing nothing on a table. It governs ripples in gravity that crossed 130 million light-years and arrived within 2 seconds of a burst of gamma rays. And in 1910, a man almost nobody has heard of derived the whole of it, the limit and the geometry, and all of it, from 4 statements about space and time, without mentioning light once. So if the number does not belong to light, what is it actually measuring? By the end of tonight, you will know exactly. Settle in. Hit subscribe if you're new here, because by the end of this, you will not be able to say the words, the speed of light, without hearing what is wrong with them. Now, let's slowly ease into this. Part 1. The number that does not belong to light. There is a number that almost everyone alive has heard at least once, and almost nobody has ever been told the truth about. The number is 299,792,458 meters per second. It has a name attached to it, and the name is the speed of light, and that name is where the trouble starts. Consider where this number shows up. Take a small object and set it on a table in front of you. A paperweight, a coin, a stone from a beach. It is not moving. Nothing is passing through it. There is no beam, no radiation, no signal, no wave of any kind involved in the situation. It is a lump of matter, sitting still, doing nothing at all. And if you want to know how much energy is locked up inside that stationary object, the equation you reach for contains the speed of light, squared, not multiplied by something to do with light, not corrected by a factor involving light. The speed of light, sitting right there at the center of an equation about a rock that is not going anywhere. Give the number some scale before we go any further, because raw figures slide off the mind. 299,792,458 meters per second works out to about 1,079 million kilometers per hour. Something moving at that rate would circle the equator of the Earth about 7.5 times in a single second. Light from the surface of the moon reaches you in 1.25 seconds. Light from the surface of the sun takes 8 minutes and 20 seconds, which means the sun you can see on a clear afternoon is always the sun as it was 8 minutes ago. From the nearest star beyond our own, the trip takes 4.25 years. And the fastest a human being has ever moved under their own power is roughly 10 meters per second, which is about 3 parts in 100 million of that number. Every instinct any of us has about how motion works was calibrated in a regime where the corrections we are about to discuss are smaller than 1 part in 100 million. Ask yourself why that should be. If the number really were a fact about light, in the way that the melting point of ice is a fact about water, then it should appear in the physics of light and nowhere else. It should show up when you calculate how a lens bends a beam, or how long a signal takes to reach a satellite, and then it should stay in its lane. Instead, it turns up everywhere. It is in the momentum of a proton, in an accelerator, which is a lump of matter with an electric charge and no particular interest in photons. It is in the equations describing the behavior of every massive field in the standard model of particle physics. It is in the mathematics of how ripples in gravity move across the universe. And gravity is not electromagnetism, and never has been. More than that. In the summer of 2017, 2 neutron stars collided in a galaxy about 130 million light-years away, and the shockwave they sent through the shape of space itself arrived at detectors on Earth. That shockwave was not light. It was not made of light. It did not involve light. It was a tremor in the geometry of the universe, the closest thing there is to a wave in nothing at all, and it traveled at exactly, precisely, the speed of light, to within about 1 part in 1,000 million. After a journey of 130 million years, it kept perfect pace with the flash of gamma rays that left the same collision at the same moment. Here is what they left out of every explanation of this you were ever given. The universe is not arranging itself around light. Space-time is not consulting photons. The reason nothing can go faster than that number is not that light got there first and set a precedent. The relationship runs the other way entirely, and once you see which way round it goes, the whole subject stops sounding like an arbitrary rule the universe happens to enforce and starts sounding like the only way a universe could possibly be built. The standard story begins with 2 statements. The first is that the laws of physics are identical for every observer who is not accelerating, which is a very old idea and a very reasonable one. The second is that light travels at the same speed for every observer, regardless of how fast the source is moving, and regardless of how fast the observer is moving. From those 2 statements, everything in special relativity follows, and the derivation is airtight, and every prediction it makes has been confirmed to accuracies that beggar description. But look at that second statement for a moment longer than usual. It says that the structure of space and time, the arena inside which every event in the history of the universe has taken place, is indexed to the propagation speed of one particular phenomenon. Electromagnetism is 1 interaction out of 4. The photon is 1 particle out of dozens in the catalogue. Why would the geometry of everything be pegged to any of them? Why would the shape of the universe care what a photon does? The answer is that it does not care, and never did. There is another route to exactly the same mathematics, the same transformation between reference frames, the same causal structure, the same absolute limit, that never mentions light at any point. Not in the assumptions, not in the derivation, not in the conclusion. It was found in 1910, 5 years after Einstein published, and it has been rediscovered independently at least half a dozen times since, and outside of specialist journals, almost nobody has ever heard of it. That route starts from 4 statements about space and time that are so mild you would struggle to describe them as physics at all. It ends with a single equation containing exactly 1 unknown number, a number the mathematics cannot pin down, and that unknown number, depending on its value, produces one of 3 completely different universes. One of them has no cause and effect in it. One of them has no matter in it. The third one is this one. Tonight we are going to build that argument from the ground up, and we are going to do it without ever once using light as an ingredient. We will start in a sealed cabin on a ship in 1632 with a bowl of fish and a dripping bottle. We will pass through the moment in 1856 when 2 men in Leipzig held the speed of light in a notebook and walked straight past it. We will find the exact point where the physics of Newton and the physics of Maxwell tore each other apart, and we will see what everyone did about it, and why what they did was right for the wrong reason. And then we will throw away the assumption that everything since has been built on, and see what stands up without it. By the end of tonight you will know exactly what that number measures, and it is not the speed of anything in particular. It is something considerably stranger and considerably more fundamental, and once you have it, the fact that light happens to move at it will look like the least interesting thing about it, a coincidence of history, a matter of which instrument human beings happen to build first. But before any of that, we have to go back to a much older idea, and to a man who was about to be put on trial for a different part of the same book. Because the whole argument rests on a principle that was written down more than 250 years before anyone suspected light had a speed at all. And the person who wrote it down was, at that moment, in very serious trouble. Part 2. The man who said no place is special. In February of 1632, a book was published in Florence, with a title that translates as Dialogue Concerning the Two Chief World Systems. Its author was 68 years old, and within a year he would be summoned to Rome, tried, made to kneel and read aloud a statement renouncing what he had written, and sentenced to spend the rest of his life confined to his own house. He would die there, blind, 10 years later, in January of 1642. The book itself would remain on the Church's list of forbidden works until 1835, 203 years after it appeared. Everyone knows what the trouble was about. The book argued, through the mouths of 3 characters having a conversation over 4 days, that the earth moves around the sun rather than sitting motionless at the center of creation. That is the part of the story that made it into the history lessons. But there is another argument buried in the second day of that dialogue, and it is the argument we need tonight, and hardly anyone outside physics has ever heard of it. The problem Galileo faced was not really whether the earth moves. The problem was that nobody could feel it moving. If the earth were racing around the sun at tens of kilometers per second, surely you would notice. Surely a stone dropped from a tower would land behind the tower's base, because the ground had slid out from under it during the fall. Surely birds would be swept off their perches. Surely the air would howl past. None of that happens, and the absence of it was the strongest argument the other side had. So Galileo answered it with a thought experiment, and he built it not as an abstraction, but as a room you could stand inside. Imagine you are shut below decks in the main cabin of a large ship. The cabin is sealed. There are no windows. With you in the room are some flies and some butterflies, moving through the still air. There is a large bowl with fish swimming in it. Hanging from the ceiling there is a bottle, and it is dripping, 1 drop at a time, into a narrow-necked jar set on the floor directly beneath it. The ship is at anchor. Everything is calm. You watch the drops fall, one after another, straight down into the neck of the jar. You watch the fish turn in their bowl, with equal ease in every direction. You throw a small object to a friend on the other side of the room, and you notice it takes the same effort whichever way you throw it. You jump, both feet together, toward the front of the cabin, and then you jump toward the back, and you cover exactly the same distance both times. Now the ship gets underway, not roughly, smoothly, steadily, in a straight line, with no waves and no shuddering, at whatever speed you like. And here is the thing Galileo asks you to notice. Nothing in the cabin changes. Not one thing. The drops still fall straight into the neck of the jar. They do not drift toward the stern while they are in the air. The flies and the butterflies do not pile up against the back wall. They move through the air as easily forward as backward, and they do not have to work harder to keep up. The fish swim as freely as before. Your jump toward the front still covers exactly as much floor as your jump toward the back. You can throw, drip, swim, fly, and jump all day, and no experiment you can perform inside that sealed room will tell you whether the ship is moving or standing still. That is the principle of relativity, in its original form, 400 years old, and still standing. It says something quite radical when you unpack it. It says that uniform motion has no local consequences at all. There is no experiment, of any kind, anywhere, that can detect it from the inside. And if motion cannot be detected from the inside, then the question, how fast am I really going, has no answer. There is no fact of the matter. You are only ever moving relative to something else, and the choice of that something else is yours. Notice how far this goes. Galileo's opponents said, the earth must be special, must be the still point at the center. He said no place is special. But the ship's cabin says something stronger than that. It says no speed is special either. There is no state of motion that counts as genuinely at rest, no absolute standard against which velocities could be measured. Every steady velocity is as good as every other. That idea, which arrived in the world attached to an argument about the solar system, turned out to be more important than the argument it was attached to. Isaac Newton took it and made it formal. In the Principia, published in 1687, he stated it as the fifth corollary to his laws of motion, and the wording is almost prim in how obvious it tries to sound. The motions of bodies within a given space, he wrote, are the same among themselves whether that space is at rest or moving uniformly forward in a straight line. Same idea, same content. Galileo's cabin, dressed in Latin and given a number. And then Newton wrote down the mathematics that connects one moving observer's description of the world to another's. And this is where we need to slow right down, because there is something hidden in it. Suppose you are standing still, and I am walking past you at some steady speed. We both want to describe the position of a bird. You measure its distance from you. I measure its distance from me. To convert between our two descriptions, you take my measurement and subtract my speed, multiplied by however long we have been at it. That is the first equation, and it is nothing more than common sense written down. If I have walked 10 meters, and I say the bird is 30 meters ahead of me, you say it is 40 meters ahead of where I started. Fine. But there is a second equation, and it is the one nobody writes on the board, because it looks too obvious to be worth stating. It says that my time equals your time. My clock reads exactly what your clock reads. However much duration has passed for you, precisely that much duration has passed for me, and it does not matter in the slightest how fast either of us is moving. Duration is duration. A second is a second for everybody, everywhere, always. From those two equations together, one consequence drops out immediately, and it is the consequence every one of us carries around as instinct. Velocities add. If you are on a train moving at 100 kilometers per hour, and you walk forward down the aisle at 5 kilometers per hour, then someone standing on the platform sees you moving at 105. If a monkey rides on the back of a skating pony, the monkey's speed relative to the ground is the pony's speed plus the monkey's own. Everyone knows this. Everyone has always known this. It has never once failed at any speed a human being has ever directly experienced. And it is wrong, not approximately wrong, not wrong in some edge case at the far end of the universe. Wrong in principle, wrong at the foundations, wrong in a way that takes the second of those two equations, my time equals your time, and destroys it completely. But nobody would have any reason to suspect that for another 200 years, and when the suspicion finally arrived, it did not come from anyone studying motion. It came from two men in a laboratory who were trying to work out what happens when you push a magnet toward a coil of wire. Part 3. Two people, two explanations, one force. Take a bar magnet in one hand and a coil of copper wire in the other. Connect the ends of the coil to a meter that will show you any current flowing through it. Now push the magnet toward the coil. The needle on the meter twitches. Pull the magnet away. The needle twitches the other way. Hold the magnet perfectly still, however close, and nothing happens at all. Michael Faraday worked this out in 1831, and it is the basis of every generator, every transformer, and every power station on Earth. Here is the question that nobody asks about it. What, exactly, causes the current? There are two answers, and the physics gives you a different one depending on which object you decide is moving. Answer 1. The coil is sitting still, and you push the magnet toward it. From the coil's point of view, the magnetic field passing through it is getting stronger with every moment. A changing magnetic field creates a circulating electric field around it. That is one of the 4 equations of electromagnetism, and it has been on the books since the 1860s. That electric field grabs the free electrons in the copper and pushes them around the loop. Current flows. The cause of the current is an electric field, created out of nothing by a magnetic field that would not sit still. Answer 2. Now leave the magnet on the bench and move the coil toward it instead. From the magnet's point of view, its own field is not changing at all. It is exactly as steady as it has ever been. There is no circulating electric field because nothing is changing. So what pushes the electrons? The answer is that the electrons themselves are now moving because they are being carried along inside a moving piece of copper, and a charge moving through a magnetic field feels a sideways shove. That shove drives them around the loop. Current flows. The cause of the current is a magnetic force on moving charges, with no electric field involved anywhere. Two completely different explanations. Two different fields doing the work. Two different mechanisms, with nothing in common except the outcome. And the outcome is not merely similar in the two cases. It is identical. The same needle moves by the same amount. If you did not know which object had been moved, there is no measurement you could make on the current that would tell you. It is worth pausing on how peculiar that already is. In almost every other part of physics, when two descriptions of the same event disagree about what is doing the pushing, one of them is simply wrong, and an experiment will eventually say which. Here, no experiment can. Both accounts predict the same current to the last decimal place, in every configuration anyone has ever tried, at every speed anyone has ever managed. The disagreement is not between a right answer and a wrong one. It is between two right answers that cannot both be describing the same underlying furniture of the world. This is not a puzzle physicists overlooked. It is the very first thing Einstein wrote about in 1905. His paper, received by the journal Annalen der Physik on the 30th of June, published on the 26th of September, and containing not a single citation to anyone else's work, opens by pointing out that the standard treatment of electrodynamics, when applied to moving bodies, leads to asymmetries that do not appear to be inherent in the phenomena. That is a very polite way of saying that the mathematics is telling two stories about something that only ever does one thing. He does not open with the famous experiment about the ether. He opens with a magnet and a coil. So which explanation is the true one? Which field is really there? The question has no answer, and the reason it has no answer is the most important thing in this part of the story. What we actually measure, in any experiment ever performed, is never a field. Fields are not the sort of thing you can put a probe on. What you measure is a force, a push on something, a deflection, a current, a needle. And the force on a charged particle has a single formula that covers both cases at once. It is the charge multiplied by the electric field, plus the charge multiplied by the particle's velocity crossed with the magnetic field. Two terms added together, one term for the electric part, one for the magnetic part. Now watch what happens when you change your point of view. Move to a different reference frame, start walking, or sit on the magnet, or ride along with the coil, and the two terms change. The electric part grows, and the magnetic part shrinks, or the other way round, depending on how you are moving. Neither term is stable. Neither has a value that everyone agrees on, but the sum of them, the total force on the particle, is exactly the same for every observer in the universe. Sit with that for a moment, because it is genuinely strange. The electric field is not a fixed property of a region of space. Neither is the magnetic field. Two observers passing through the same point, at the same instant, moving differently, will honestly and correctly write down different values for both. Where one of them sees a pure magnetic field and no electric field at all, another sees a mixture of both. Neither of them is making a mistake. Neither is using the wrong instrument. They are both measuring reality accurately, and reality is giving them different numbers. What they agree on is the force. Two people, two explanations, one force. The resolution, worked out properly only after relativity arrived, is that the electric field and the magnetic field are not two things. They are one thing, and the split between them is not a fact about the universe. It is a fact about the observer. There is a single geometric object that carries all the electromagnetic information at a point in space-time, and when you look at it from a particular state of motion, it presents itself to you as some amount of electricity and some amount of magnetism. Change your motion, and the same object presents a different mixture. The way the length of your shadow is not a property of you, and not a property of the pavement, but a property of where the sun happens to be. And this matters for tonight, far beyond electromagnetism, because it is the first proper lesson in a habit of mind we are going to need. The lesson is that some quantities in physics that feel absolutely obviously real as anything gets, real enough that we teach children to draw them with arrows, turn out on inspection to be observer-dependent projections of something deeper. The thing that is actually real is the thing everybody agrees on. Hold on to that criterion, because we are going to use it again, and the next time we use it, the stakes will be considerably higher than a twitching needle. If the electric and magnetic fields, which every physics course treats as the furniture of the universe, are merely two shadows of a single object cast at different angles, then when we find a quantity that every observer in the universe agrees on exactly, without exception, no matter how they are moving, we should sit up. Those are rare. Those are the things the universe is actually made of. But before we get there, we need to look at what this frame-shuffling business does at ordinary speeds, in ordinary objects, in your own house. Because the standard assumption is that relativity is something that happens to spaceships and particle beams and things falling into black holes, that it is a correction so tiny at human speeds that it may as well not exist. That assumption is about to fall apart, and it is going to fall apart in the most domestic setting imaginable. A length of copper wire, carrying an ordinary current, with electrons inside it, drifting along more slowly than a snail. Part 4. The magnet on your fridge is a relativistic machine. There is a wire somewhere near you right now, with a current running through it. In the wall, in a lamp flex, in the charger on the table. Picture what is happening inside it. Most people, if they picture anything at all, imagine electrons streaming down the copper at something like the speed of the electrical signal, which is a substantial fraction of the speed of light. That picture is wrong, and how wrong it is turns out to matter enormously. The signal moves fast, the electrons do not. In a copper wire carrying an ordinary household current, the individual conduction electrons drift along at roughly 1/10,000th of a meter per second. That is a few centimeters per hour. If you could paint one of them and watch it, it would take the better part of a day to travel the length of a lamp cord. The electricity arrives instantly, for the same reason water arrives instantly from a tap that is already full. The pipe was never empty. The electrons were already everywhere along the wire, and they all start shuffling at once. Now here is the setup that makes this part of the story work, and it comes from Edward Purcell, who put it at the heart of his electromagnetism textbook in 1965, and thereby quietly changed how a generation of physicists understood what magnetism actually is. Take that current-carrying wire and consider it from the laboratory. It is electrically neutral. The copper lattice is a fixed grid of positive ions, and threaded through it is a sea of negative conduction electrons, and the two charge densities cancel exactly. A voltmeter placed anywhere near it reads nothing, because there is no net charge to push on anything. But if you send another charged particle flying past the wire, parallel to it, that particle feels a force, the magnetic force, produced by the current, exactly as described in every textbook. Now change your seat, get up, and travel alongside that flying charge, matching its speed exactly, so that in your new frame, the particle is sitting still. And immediately something must give, because a stationary charge cannot feel a magnetic force. The formula has the particle's velocity in it, and the velocity is now 0, so the magnetic term is gone. It is simply not there anymore. Yet the particle is obviously still being pushed. You can watch it accelerate, and no change of seat can unaccelerate it. What has happened is that the wire is no longer neutral. In your new frame, the positive lattice and the drifting electrons are moving at different speeds than they were before, and the amount by which each of them is squeezed along the direction of travel is therefore different. The positive charges get packed slightly closer together than the negative ones, or slightly further apart, depending on which way the current runs. The exact cancellation breaks. The wire acquires a small net charge, and that net charge produces an ordinary electric field, and that electric field pushes on the stationary particle with a force of exactly the size the magnetic force had in the other frame. The magnetic force did not vanish. It got renamed. In one frame it is magnetism, in another it is electrostatics, and both observers measure the same push on the same particle. That is worth restating plainly, because it is one of the most underappreciated facts in physics. Magnetism is not a separate force of nature. Magnetism is what electrostatics looks like when the charges are moving and you take the geometry of space and time seriously. There are not two phenomena here that happen to be related. There is one phenomenon, and the second name is an artifact of your point of view. And now for the numbers, because the numbers are where this stops being a clever argument and starts being unsettling. The relativistic correction factor, at a speed of 1/10,000th of a meter per second, is almost inconceivably small. Work it out, and you get a departure from ordinary, everyday behavior of roughly 5 parts in 100,000 million, 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 million. That is a correction of about 1 part in 10 to the 26th. To put that in some kind of perspective, it is a smaller fractional adjustment than the width of a single atom compared to the distance across the solar system. By any normal standard, a correction that size is not a correction. It is 0 with extra steps. But look at what it is being applied to. A cubic meter of copper contains something like 85,000 million 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 free conduction electrons. Multiply that by the charge on each one, and the negative charge sitting in every cubic meter of an ordinary copper wire comes to about 13,600 million coulombs. There is an equal and opposite mountain of positive charge in the lattice, cancelling it. For scale, a bolt of lightning transfers on the order of 15 coulombs. The charge hiding inside 1 cubic meter of ordinary copper in each sign is roughly 1,000 million lightning strikes worth, held in perfect balance. Take a correction of 1 part in 10 to the 26th and apply it to a quantity that large, and what falls out the other side is a force strong enough to hold a photograph to a fridge door. The reason this works is that the electric force is monstrously strong, and we almost never see it undisguised. Between 2 protons, the electric repulsion is something like 10 to the 36th times stronger than the gravitational attraction, a 1 followed by 36 zeros. We do not notice that strength in daily life only because matter is so scrupulously neutral. Every positive charge is shadowed by a negative one, and the two cancel to extraordinary precision everywhere you look. Break that cancellation by even 1 part in 100,000 million 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 million, and you have unleashed something that can compete with the gravitational pull of an entire planet, which is exactly what a fridge magnet does when it hangs a photograph in defiance of the Earth. That is what a magnet is. That is what has been happening every time you have picked one up since you were a child. The relativity of space and time, operating at a speed slower than a snail's, multiplied by a charge density so enormous that a correction in the 26th decimal place becomes a force you can feel between your fingers. Follow that where it goes. Every electric motor in the building you are in the fridge, the fan, the pump, the hard drive, the vibration in a phone, is a machine whose entire operating principle is a relativistic effect. Every generator in every power station on the planet is running on the same effect, at the same absurd scale of tiny correction times enormous charge. Every loudspeaker converting a current into a sound in your ears is doing it. The whole electrified world, the entire 20th century, runs on relativity, and it has been doing so since decades before anyone had the faintest idea that space and time were connected. So the standard framing has it backwards in a second way. Relativity is not the physics of the extreme. It is not something reserved for objects near black holes or particles in accelerators. It is in the wall behind you, at walking pace, doing something so ordinary that nobody thinks to ask why it works. And that ought to change how the next question sounds. If the deep structure of space and time is already showing up in a fridge magnet, then the constant at the center of that structure is not some remote cosmic speed limit that only matters at the far edges of physics. It is a number that is already involved in your evening, which makes it all the more urgent to ask where the number came from in the first place. And it came from a place nobody expected, not from measuring light, but from two men in Leipzig discharging a jar. Part 5. The Equations that Refuse to Transform. Leipzig, 1856. Wilhelm Weber and Rudolf Kohlrausch are in a laboratory with a Leyden jar, which is a glass vessel lined inside and out with metal foil, the earliest device human beings built for storing electricity. They are not thinking about light. Light does not enter their reasoning at any point. Their problem is a bookkeeping problem. There are two entirely separate ways of counting how much electricity you have. The first way comes from electrostatics. You take two charges, measure the force between them, and define your unit of charge from that force. The second way comes from magnetism. You take two wires carrying currents, measure the force between them, and define your unit of charge from that force instead. Both are perfectly good definitions. Neither one has anything to do with the other. But the same physical quantity of electricity, measured both ways, comes out as two different numbers, and Weber and Kohlrausch want to know the ratio between them. So they charge the jar, they discharge it, they measure it one way, then the other, and they work the ratio out on paper. The number they arrive at is 3.107 times 10 to the 8th in meters per second. Watch that number sitting on the page for a moment. Nothing in the experiment involved a beam of light. Nothing involved a lamp, a mirror, a lens, a telescope, or a distant star. Two men measured the force between charges and the force between currents, took a ratio, and wrote down a speed within a few percent of the speed of light, and neither of them looked twice at it. Gustav Kirchhoff noticed the following year that signals in a wire with no resistance ought to travel at that same rate, and remarked on it, and the world moved on. It took James Clerk Maxwell to say the obvious thing out loud. Across a series of papers in the early 1860s, Maxwell assembled the laws of electricity and magnetism into a single connected system, and out of that system fell a prediction. The fields should be able to support a self-sustaining wave, a disturbance in which a changing electric field creates a magnetic field, which creates an electric field, propagating outward with no medium doing anything visible. And the speed of that wave was fixed entirely by two constants of the laboratory bench. One of them describes how strongly charges push on each other in empty space. The other describes how strongly currents pull on each other. That is all. Take one, multiply by the other, take the square root, and turn it upside down, and you have a speed. Neither constant was measured with light. One comes from static electricity, the other from magnets. And yet the speed they produce together is the speed of light. And Maxwell wrote that we can scarcely avoid the inference that light consists of transverse undulations of the same medium that carries electricity and magnetism. It is worth naming those two constants, because their provenance is the whole point. The first is the permittivity of free space. A number close to 8.85 times 10 to the minus 12 in the standard units. And you get at it by measuring how hard two stationary charges push each other apart. The second is the permeability of free space, close to 1.257 times 10 to the minus 6, and you get at it by measuring how hard two parallel wires carrying current pull each other together. Charges on a bench, wires on a bench, both measurable by a patient person in a room with no windows, working entirely in the dark. And the combination of those two bench numbers is a speed that nothing in the universe can exceed. He never lived to see it confirmed directly. Maxwell died in 1879 at the age of 48, 7 years before Heinrich Hertz generated electromagnetic waves in a laboratory with a spark gap and detected them across a room, and measured their speed, and found it was exactly what the equations had said. So by the 1880s, physics had two magnificent structures: Newton's mechanics, which had been correct about every moving object for 200 years, and Maxwell's electromagnetism, which had unified electricity, magnetism, and light into one system, and predicted a whole invisible spectrum nobody had suspected. There was a widespread sense that the work was nearly finished. And then somebody put the two structures side by side and did the obvious check. Remember what the principle of relativity demands. The laws of physics must look the same in every frame moving steadily. So take Maxwell's equations, apply the conversion between a stationary observer and a moving one, the one with the innocent second line that says everybody's clock agrees, and see whether the equations come out looking the same on the other side. They do not. They come out mangled. Extra terms appear that have no business being there. The wave equation that predicted light acquires cross terms that ruin it. The clean symmetry between electricity and magnetism breaks. Whatever those transformed equations describe, it is not the same physics. Which means that if Newton's conversion between frames is correct, then Maxwell's equations can only be true in one special frame of reference, and in every other frame they are wrong. That is a catastrophe, and there are only 3 ways out of it. The first way out: Maxwell is wrong. His equations are an approximation that happens to work in our particular circumstances, and the real laws of electromagnetism are something else that behaves properly. Nobody could make this work. The equations were too successful, too precise, and too productive. They had predicted radio. The second way out: Galileo is wrong. The 250-year-old rule for converting between moving observers, the one that says velocities add and clocks agree, is not the correct rule. This possibility was barely considered because it looked insane. It amounts to saying that duration itself depends on how fast you are going. The third way out: there is a special frame after all. Maxwell's equations are exactly true, but only with respect to the medium that light waves in, the luminiferous ether, and in any frame moving relative to that medium, you would measure a different speed for light, exactly as a sound wave travels at different apparent speeds if you run toward or away from it. This was the option almost everyone took, and it was entirely reasonable. Every other wave anyone had ever studied waved in something. The third option had a testable consequence. If the Earth is moving through the ether, then light should travel a little faster in one direction than another, and an instrument sensitive enough would catch it. In 1887, in a basement in Cleveland, Albert Michelson and Edward Morley built that instrument. They split a beam of light in two, sent the halves down perpendicular arms, bounced them back, and recombined them, watching for the interference fringes to shift as the apparatus rotated. To keep it steady, they mounted the whole thing on a sandstone slab about 1.5 meters square, floating in a trough of mercury, so it could be turned smoothly without a tremor. The predicted shift was about 4/10 of a fringe. What they measured was under 1/100th, roughly 40 times smaller than the prediction, and consistent with nothing at all. There was no ether wind, there was no detectable motion through the medium. Michelson had set out to measure how fast the Earth is moving through the stuff that light waves in, and instead he had established that the question does not have an answer. He regarded it as a failure for most of his life, which is a hard thing for a man who became the first American to win a Nobel Prize in the sciences. So the third option was gone, and only the second option was left standing, the insane one, the one that says Newton's rule for converting between observers is simply wrong. Someone was going to have to write down a better rule, and several people did. That is the part of the story everyone thinks they know, and it is where the mistake we are chasing tonight actually gets made. Part 6. The wrong question everyone asked. The right mathematics was written down 3 separate times by people who did not believe it. Waldemar Voigt got there first, in 1887, the same year as the Cleveland experiment. He was working on the mathematics of wave equations and elastic media, and he wrote down a transformation between reference frames that was very nearly the correct one, off by an overall factor, but with all the essential structure in place, including the alarming part where the time coordinate gets mixed up with the space coordinate. He did not think he had discovered anything about the nature of time. He thought he had found a useful substitution for solving a differential equation, and he moved on. George Fitzgerald, in 1889, suggested that the Cleveland null result could be explained if objects moving through the ether physically shrink along their direction of motion by precisely the amount needed to hide the effect. Hendrik Lorentz proposed the same thing independently in 1892. It was, on its face, an outrageous patch, a contraction with no mechanism, invented for the sole purpose of concealing something everyone was sure was there. Joseph Larmor in 1897, and Lorentz again in 1899 and 1904, worked the idea into its full form. By 1904, Lorentz had the entire transformation, correct in every detail, the exact equations that appear in textbooks today, and he called one of the quantities in it local time, and he was explicit about what he thought it was: a mathematical convenience. A bookkeeping trick that let you calculate in a moving frame while real time, true time, went on ticking uniformly in the ether. The equations were exactly right, and the story attached to them was exactly wrong. Henri Poincaré came closest to seeing it. In a note presented to the French Academy of Sciences on the 5th of June 1905, and then in a longer paper published in Palermo the following month, he showed that these transformations form what mathematicians call a group, that combining any 2 of them gives you another one from the same family, that each has an inverse, that the whole set is closed and self-consistent. He identified the quantity that stays fixed under all of them, and he gave the transformations their name, calling them the Lorentz transformations, after the man who had written them down without believing what they meant. Hold on to that word, group. We are going to need it very soon, and it is going to do more work than anyone in 1905 realized. A group, in this sense, is not a collection of people. It is a set of operations that behave sensibly together. Perform 2 of them in a row, and you get a third from the same set. Every one of them can be undone, and doing nothing counts as one of them. It sounds like a technicality. It is going to turn out to be one of the 4 pillars holding up the entire universe. Then came the paper everyone remembers, received on the 30th of June, 1905, from a 26-year-old technical expert 3rd class at the patent office in Bern, who had been turned down for every academic job he had applied for. The paper cites no sources. Its title mentions electrodynamics and moving bodies, not relativity, and it begins, as we have already seen, with a magnet and a coil. What Einstein did was not to find new equations. Lorentz already had those. What Einstein did was to stop apologizing for them. He said, "Take these 2 statements as true, and everything follows without needing an ether at all." Statement 1. The principle of relativity. The laws of physics are the same in every frame moving uniformly. That is Galileo's ship, 400 years old, unchanged. Statement 2. the constancy of the speed of light. Light travels at the same speed in empty space for every observer, regardless of how the source is moving and regardless of how the observer is moving. From those two, the whole of special relativity drops out. Time dilation, length contraction, the collapse of universal simultaneity, the impossibility of reaching the limit, all of it, forced, with nothing left over. It is one of the tightest pieces of reasoning in the history of the subject, and the second statement is doing an enormous amount of the lifting. Now, look at that second statement with fresh eyes. It is a statement about light. Specifically, it says that the entire structure of space and time, the arena inside which every event that has ever happened, has its geometry set by how fast a particular kind of ripple in the electromagnetic field happens to propagate. Electromagnetism is one interaction among four. The photon is one entry in the particle catalogue, and we are being asked to accept that the shape of the universe is pinned to it. The oddness becomes sharper if you imagine the postulate written about anything else. Suppose a physicist stood up and announced that the geometry of space-time is determined by the propagation speed of sound in iron, or by the drift rate of a particular chemical reaction, or by how quickly a certain species of neutrino changes flavor. You would ask, immediately and reasonably, why that phenomenon? Why should the universe be built around that? The only reason the same question does not get asked about light is that we have heard the claim so many times that it has stopped registering as a claim at all. Familiarity has done the work that argument should have done. There is a reason it happened this way, and the reason is entirely historical. In 1887, light was the only thing anybody could measure that moved fast enough for the effects to show up. Nobody had detected a gravitational wave. That would take another 128 years. Nobody had a particle accelerator. Nobody had an atomic clock. Light was the one messenger available, so light got its name on the constant, and the postulate got written in terms of the only phenomenon anyone could test. But a postulate is not an explanation. It is a place you agree to start. And when a theory has a postulate in it that seems strangely specific, when the foundations of the universe appear to be indexed to one particular phenomenon out of thousands, that is usually a sign that the postulate is not fundamental. It is a symptom of something underneath that nobody has articulated yet. So here is the question that almost nobody asks. What if the constancy of light's speed is not an input at all? What if it is an output, a consequence of something more basic, something that has nothing to do with electromagnetism, something that would have been true even in a universe with no light in it whatsoever? What if light is the passenger, not the road? That is not a rhetorical flourish. It is a claim that can be tested, and the test is simple to describe. Throw the second postulate away, delete it, refuse to assume anything at all about light or about electromagnetism or about any specific phenomenon. Keep only statements about space and time themselves, statements so mild that any physicist from any century would sign them without hesitation. Then do the algebra and see what you are left with. If what comes out is nothing, if the assumptions are too weak to determine anything, then the light postulate really was load-bearing, and the standard story is right. But if what comes out is the Lorentz transformation, in full, with a universal speed limit sitting in it that nothing can cross, then the light postulate was never necessary. It was a shortcut, a ladder we climbed, and then forgot to throw away, and we have been teaching the ladder as though it were the building. That calculation was done in 1910 by a man almost nobody has heard of, and it comes down to 4 statements. Not one of them mentions light. Part 7. 4 things that must be true. The man's name was Vladimir von Ignatowski, and in 1910 he published a paper in the Physikalische Zeitschrift with a title that translates as something like A few general remarks on the principle of relativity. Philipp Frank and Hermann Rother published an independent version the following year. The argument has been rediscovered and republished at intervals ever since, most cleanly by Jean-Marc Lévy-Leblanc in 1976, in a paper he simply titled One More Derivation of the Lorentz Transformation, and by David Mermin in 1984 under the heading Relativity Without Light. Each time it appears, it is treated as a charming curiosity. Each time, the textbooks go on opening with the light postulate. Here are the 4 things the argument assumes. Listen to how ordinary they sound. The first is that space and time are homogeneous. This means the laws of physics do not depend on where you are or when you are. An experiment performed in this room today gives the same result as the identical experiment performed a kilometer away, or tomorrow, or on the far side of the galaxy in 1,000,000 years. Not a similar result, the same one. You may think this is a modest assumption. It is in fact the assumption on which the entire enterprise of science rests. If the laws changed from place to place, no measurement made anywhere would tell you anything about anywhere else, and there would be no such thing as a law at all, only a catalogue of local behaviors. Every time an astronomer works out the composition of a star from its spectrum, they are relying on the claim that hydrogen 10,000 light-years away obeys the same rules as hydrogen in a laboratory in Munich. It has never once failed. Homogeneity has a sharp mathematical consequence, and this is the part that matters. It forces the conversion between reference frames to be linear, meaning that positions and times can be multiplied by constants and added together, but never squared, never fed into anything curved or bent. Here is why. Suppose the conversion were not linear. Then an object moving at a perfectly steady speed with nothing pushing it would, when described from another frame, appear to speed up or slow down, depending on where it happened to be in space. A free particle would accelerate for no reason, and the reason it accelerated would be its location. That is exactly what homogeneity forbids. So the transformation is linear, and that single word eliminates almost every mathematical possibility before we start. The second assumption is that space is isotropic. There is no preferred direction. The laws of physics do not care which way you are facing. Turn your entire laboratory around, run the experiment again, and nothing changes. This too has been tested to an extraordinary degree. Searches for directional dependence in atomic energy levels have pushed the limits to parts in 10 to the 20-something. And it too has a consequence for our transformation. It means the rules for a boost in one direction have to be the mirror image of the rules for a boost in the opposite direction, and that the coefficients in the transformation can depend only on how fast you are going, never on which way you happen to be pointed. The third assumption is the principle of relativity itself. No inertial frame is privileged. Galileo's cabin, Newton's fifth corollary. There is no state of steady motion that counts as truly at rest, and therefore the description that I write of you must have exactly the same form as the description you write of me. That symmetry is called reciprocity, and it is worth pausing on because it does more work than it appears to. If I see you moving away at some speed, you must see me moving away at the same speed in the opposite direction. Not a different speed, not a speed corrected by some factor, and the mathematical machinery you use to translate my measurements into yours must be the identical machinery I use to translate yours into mine, with only the sign of the velocity flipped. If it were not, if my conversion were somehow different in form from yours, then one of us would be in a special frame, and the whole principle collapses. There is a beautiful side note here that is worth a moment, because it shows how much these two assumptions have already been quietly doing for physics. In 1918, Emmy Noether proved that every continuous symmetry of a physical system corresponds to a conserved quantity. The symmetry of the laws under shifting in time gives you conservation of energy. The symmetry under shifting in space gives you conservation of momentum. The symmetry under rotation gives you conservation of angular momentum. which means the first two assumptions on our list, the uniformity of space and time, and the absence of a favored direction, are the same assumptions that make energy, momentum, and angular momentum conserved quantities in the first place. We are not reaching for anything exotic. We are using the same two statements that already underwrite the most reliable accounting rules in all of science. The fourth assumption is the group property. This is the one Poincaré spotted, and it is the quietest of the four, and possibly the most powerful. It says that transformations between frames compose consistently. Suppose I want to describe things from the point of view of a fast-moving particle. I could do it in one step, or I could do it in two steps. First convert to the frame of something moving moderately fast, then convert again from there. The requirement is simply that both routes give the same answer. It also says that if I convert from my frame to yours, and then convert back, I have to end up exactly where I started, with nothing left over. And it says that the conversion for zero velocity does nothing at all. Say that out loud, and it sounds like the most trivial demand imaginable. Of course, going there and coming back should get you home. Of course, 2 short trips should equal 1 long one. But this is a genuine constraint, and most conceivable transformations fail it. It is the mathematical way of saying that the universe is consistent with itself, that there is one reality being described from different angles, rather than a collection of incompatible descriptions that happen to overlap. So there they are. Space and time are uniform. Space has no favorite direction. No velocity is special. Descriptions compose consistently. Look at that list and notice what is absent. There is no mention of light. There is no mention of electromagnetism. No mention of photons. No mention of the ether. No mention of any wave, any field, any particle, any force. There is no experimental result in there at all. Not Cleveland, not Fizeau, not Römer, not a single measurement of anything. There is nothing in the list that a physicist from any century would refuse to sign. Newton would have signed all 4 without hesitation. So would Galileo. So would anyone working today. These are not statements about the contents of the universe. They are statements about the container. And now we do the algebra. You take those 4 requirements, write down the most general transformation that could possibly satisfy them, and grind through the constraints one at a time, eliminating everything they forbid. The mathematics is not difficult. It is the kind of thing a determined undergraduate can do in an afternoon, and it fits comfortably on 2 sides of a page. What comes out the other end is a single family of transformations. Not many families. 1. And that family has exactly 1 number in it that the 4 assumptions cannot determine. 1 free parameter. 1 dial the argument leaves unset. And depending on where that dial sits, you get a completely different universe. Part 8. 1 dial, and it had to be set. Let us step back for a moment and put the pieces we have on the table together, because we have covered a lot of ground, and the next stretch is the important one. We started with a number that keeps appearing in equations that have nothing to do with light, in the energy of a stationary object, in the motion of massive particles, in the propagation of ripples in gravity. We watched Galileo establish, in a sealed cabin with a bowl of fish, that no experiment can detect uniform motion from the inside, which means no velocity is privileged. We watch the electric and magnetic fields turn out to be 2 projections of one object, with the split between them determined by nothing more than the observer's motion, and we found that the same effect, at the speed of a drifting electron, is what holds a photograph to a fridge. We watched Maxwell's equations refuse to survive Newton's rule for converting between observers, and we watched the ether get proposed to save the situation and then fail to show up in Cleveland. And we watched 4 people write down the correct replacement for Newton's rule while attaching the wrong story to it, until Einstein cleaned it up by assuming something about light. Now we have thrown that assumption away and replaced it with 4 statements about the uniformity and consistency of space and time. And we are about to find out what those 4 statements are worth. Here is what the algebra gives you. The transformation that converts one observer's measurements into another's turns out to have a specific shape. The new position is the old position minus velocity times time, all multiplied by a scaling factor. That much is familiar. It is Galileo's rule, with a stretch applied to it. But the second line is not familiar at all. The new time is the old time, minus a term that contains the velocity multiplied by the position, again with the same scaling factor out front. Read that second line again, because it is the whole revolution in one clause. The time coordinate now depends on where you are, not just on when, on where. 2 clocks, both perfect, both stationary in my frame, one here and one across the room, will not agree with each other, according to somebody moving past. The universal, uniformly flowing time that Newton wrote into the scholium of the Principia has just been deleted. And it has been deleted not by any experiment, not by any measurement of light, but by 4 statements about symmetry. Now, the scaling factor. It comes out as 1 divided by the square root of 1 minus a certain constant multiplied by the velocity squared. That constant is the crux of everything. Call it k. It appears in exactly 2 places, in the scaling factor and in the second line as the coefficient that mixes position into time. Its units are 1 over a velocity squared, which means 1 over k is a speed squared, which means k secretly contains a speed. And the 4 assumptions cannot determine what k is. They tell you that some such constant must exist, that it must be the same for everybody, everywhere, in every direction, and at every time. They tell you it is universal. They cannot tell you its value. The symmetry of space and time builds the entire structure, walks you all the way to the door, and then hands you a dial it has no power to set. Sit with that for a moment, because it is one of those places where physics stops being a description and starts feeling like a decision that was made. 4 assumptions so mild that denying any of them would make experimental science impossible have just constructed the geometry of the universe. They have told you that time and space mix, that duration is not universal, that the whole Newtonian picture of a uniform clock ticking everywhere at once is wrong. That is an enormous amount of structure to extract from statements about uniformity. And then, at the very last step, the argument runs out. There is 1 number left over, and nothing in mathematics can supply it. The universe had exactly 1 free parameter, and something had to set it. Before we look at the options, there is one more thing the algebra hands over, and it is the piece that will matter most later. The transformation also fixes how velocities combine. Put a monkey on a skateboard on the back of a rollerblading pony, to borrow an image, and ask how fast the monkey is going relative to the ground. The rule that falls out is not the rule everyone learns. It is not simply the pony's speed plus the monkey's speed. It is the pony's speed plus the monkey's speed, divided by 1 plus k, multiplied by the 2 speeds together. That denominator is new, and everything hangs on it. If k happens to be 0, the denominator becomes 1, the division does nothing, and you are back to plain addition, the rule that has never failed at any speed anyone has directly experienced, because at walking pace k times 2 ordinary velocities is a number so small it might as well not be written down. But if k is not 0, the denominator grows as the speeds grow, and the sum gets shaved down. Every addition of speed returns a little less than you put in, and the faster things are already going, the more the universe skims off the top. Nobody had to insert that behavior by hand. It was not put in to explain an experiment. It fell out of the demand that transformations compose consistently. So what are the options? There are 3, and they are distinguished by nothing more than the sign of k. The first option is that k is negative. Work through what that does to the transformation, and the square root turns into 1 plus something, and the mathematics stops being anything strange and becomes something entirely familiar. an ordinary rotation. Not a rotation in space, but a rotation that treats time as simply another direction, no different from left or up. Time becomes a fourth axis, geometrically indistinguishable from the other three. The second option is that k is exactly 0. Put 0 into the scaling factor and it becomes 1. Put 0 into the second line and the term containing the position disappears entirely, leaving new time equals old time. Everyone's clock agrees. Velocities add the way common sense says they do. This is Galileo's transformation. Precisely, the one Newton built 2 centuries of mechanics on. It has not been refuted by the derivation. It is sitting right there as one of the 3 permitted answers. The third option is that k is positive. In that case, 1 over the square root of k is a speed, a specific, finite speed, and something remarkable happens to it. Feed that speed into the velocity composition rule, and it comes back out unchanged. Add anything to it, and you still have it. Every observer, no matter how fast they are moving, measures the same value for that one speed. It is invariant, and nothing moving below it can ever be pushed above it, no matter how hard or how long you push. 3 signs, 3 universes. And notice what has still not entered the conversation. Light, electromagnetism, photons, waves, the ether, or any experiment ever performed. We have got here entirely from the proposition that space is uniform, has no favorite direction, plays no favorites among steady velocities, and permits consistent translation between points of view. That already demolishes the standard framing. The Galilean transformation is not a rival theory that Einstein overthrew. It is one of the 3 cases, the case where k equals 0, the case where the invariant speed is infinite. Newton was not wrong about the structure. He was wrong about one number, and he could not have known, because the value of that number is invisible at every speed a human being had ever observed. But now the question sharpens into something much more interesting than who was right. The question becomes, why this one? What forced the universe to pick the third case? And the answer, when you find it, turns out to have nothing to do with light, and everything to do with whether anything can happen at all. Part 9. Why the dial could not be set to 0. Start with the negative case, because it is the one that dies fastest, and for the most interesting reason. If k is negative, boosts become ordinary rotations. Time is just another direction, mathematically identical to left and up, and moving faster is exactly like turning a corner. That sounds elegant. It sounds like the kind of unification physicists dream about, space and time not merely mixed, but made genuinely interchangeable. Follow it through, and it turns lethal. The trouble is that rotations come back around. Turn through a full circle, and you return to where you started. So in this universe, velocity composition is periodic. Keep adding speed in the same direction, and eventually you come all the way round and find yourself back at rest, having accelerated continuously the entire time. Push a little further, and you are moving backwards. That alone should worry you. But the real damage is worse, because if time is a direction you can rotate into, then you can rotate a direction that points into the future until it points into the past. In such a universe, the order of events is not fixed. Given enough acceleration, any observer could turn any effect around in front of its cause. There would be no fact of the matter about which of 2 events happened first, even for events that directly produce one another. A message could be sent to arrive before it was written. A collision could scatter particles that had not yet approached. That is not a universe with unusual physics. It is a universe with no physics, because physics is a set of statements about what leads to what, and in a world where the ordering of connected events is negotiable, nothing leads to anything. The negative case is ruled out by causality itself. The sign of that one constant is fixed, not by any measurement, but by the requirement that effects follow causes. There is a formal version of this argument that physicists reach for whenever the subject of exceeding the limit comes up. and it is worth having in your pocket. In 1970, Gregory Benford, David Book, and William Newcomb published a short paper describing what they called the tachyonic antitelephone. The construction is this: if any signal could travel faster than the invariant speed, then by sending one such signal from you to a friend who is moving relative to you, and having them send one straight back, the reply arrives before the original message was sent. Not metaphorically, arithmetically. The two moving observers disagree about the ordering of the events, and faster-than-light signaling turns that disagreement into a working machine for sending information into your own past. Faster-than-light communication and consistent cause and effect cannot both exist. You may have one. So we are down to two. Either k is 0, giving Galileo's universe with an infinite speed limit, or k is positive, giving a finite one. And you might reasonably assume that the 0 case is the safe, sensible, boring option. The universe of common sense, where velocities add and clocks agree, and there is no cosmic barrier to anything. It is the universe everybody's intuition already lives in. What could possibly be wrong with it? Let us go and stand in it and find out. Step into the universe where k is 0. The first thing you notice is that nothing is far away, not because the distances are small, they are whatever they are, but because there is no delay in anything. A signal from the other side of the cosmos arrives at the instant it is sent. Every point in this universe is in immediate contact with every other point, right now, with nothing in between. There is no such thing as over there, in any sense that has consequences, because the moment anything happens anywhere, everything everywhere already knows. Reach out to touch something, and there is no interval between the reaching and the touching. Look up, and you are not seeing the past, because there is no past to see. The light, if there were light, would be arriving as it left. Every star in this sky would be showing you its present, and so would every galaxy, and so would the furthest thing there is. There is no history written into distance here. Nothing has ever taken time to arrive, because nothing takes time. Then look for something to touch in the first place, and you find that there is nothing. The reason is brutally simple. In this geometry, the energy required to give an object any mass at all becomes infinite. Mass and energy are related through the invariant speed, and if that speed is infinite, then any amount of mass, however small, costs everything there is. So there is no matter in this universe. No atoms, no dust, no stars. Nothing has mass, which means everything travels at the invariant speed, which is infinite, which means everything is everywhere at once. Reach for a magnet, and there is no magnetism either. We saw why in the copper wire the magnetic force is a relativistic effect, a correction of order, the velocity squared, divided by the invariant speed squared. Set that invariant speed to infinity, and the correction goes to 0, exactly. No magnetism, no motors, no generators, no dynamos, and no light either, because light is the self-sustaining handoff between a changing electric field and a changing magnetic field, and one of the two partners in that exchange has just ceased to exist. Stand in this universe and try to describe an event. You cannot. An event needs a here and a there to be distinguished from, and a before and an after to sit between. This universe has neither. It is one infinitesimal, undifferentiated present, in perfect and instantaneous contact with itself, containing no matter and no separation, and nothing that could be said to happen. And notice one last thing before we leave. In this universe, there is no such thing as elsewhere. In ours, every event divides the rest of the universe into three parts: the things that could have caused it, the things it could go on to affect, and an enormous middle region that can do neither, places too far away, in the time available, for any influence to have crossed between them. That middle region is where most of the universe always is, relative to you. It is the reason the sky is a record of the past, rather than a live feed. With an infinite signal speed, that middle region shrinks to nothing. Everything is causally connected to everything, at every instant, which sounds intimate, and is in fact the same thing as saying that nothing is distinguishable from anything. Come back out of it. That is what the common sense option actually looks like when you take it seriously. The universe of Galileo and Newton, the one every intuition we have is built for, is not a slightly simplified version of ours. It is a universe in which nothing exists and nothing occurs. Newton's mechanics were, without anyone knowing it, quietly assuming an infinite signal speed, and if that assumption had been literally true, there would have been no Newton, no Apple, and no room to sit in. So the dial could not be set to 0, and it could not be set below 0. Negative kills cause and effect. 0 kills matter, magnetism, light, distance, and events. Only the third case survives, and the third case is a universe with a finite, universal, invariant speed that every observer measures identically, and nothing can be pushed past. Notice what has just happened to the question. We started out asking why the universe imposes a speed limit, as though a limit were a restriction, a rule imposed on a world that would otherwise be freer without it. It is the opposite. The finiteness of that speed is the reason there is anything here to be restricted. Without it, there is no mass to move, no distance to move across, and no order in which things could move. Which means the constant is not really a speed limit at all. It is closer to a founding condition. And once you see it that way, the obvious next question is what it is actually the speed of. Because whatever it is clearly not light. Part 10. The speed of cause and effect. We have one surviving universe and one surviving constant, and now we need to work out what job it does. Go back to the criterion we picked up from the magnet and the coil, because it is about to pay off. Two observers gave completely different accounts of why a current flowed. One blamed an electric field, one blamed a magnetic force, and both were correct, because the fields are observer-dependent projections. What they agreed on was the force. And the lesson we took was that the things everybody agrees on are the things the universe is actually made of. So ask the obvious question of our new geometry. Once time and space are mixing into each other, once two clocks in the same room can disagree according to somebody walking past, once lengths and durations have all become matters of perspective, what is left that everyone agrees on? The answer is a single quantity, and it has a strange shape. Take the distance between two events in space, square it. Take the time between them, square it, and multiply by the invariant speed squared. Then subtract the second from the first. That number, the space-time interval, is identical for every observer in the universe, no matter how they are moving. It is Pythagoras with a minus sign, and that minus sign is doing all the work. It is the entire difference between space and time. If it were a plus, time would be just another direction, and we would be back in the negative k universe, where causality dies. The minus is what makes time different in kind from the three directions you can walk in, and the invariant speed is the exchange rate that lets you subtract seconds from meters in the first place. Now use that quantity to sort the universe. Pick any event, this moment, here. Every other event in the history of the universe falls into exactly one of three categories, and which category it falls into is something all observers agree on absolutely. The first category contains events that can reach you. Enough time has passed, given the invariant speed, for an influence to have crossed the distance between there and here. Everything you have ever seen, heard, felt, or been affected by is in this category. It is your past in the only sense that matters. The second category contains events you can reach. There is enough time for something leaving here and now to arrive there. That is your future, and it is the entire domain of anything you will ever do. The third category is everything else. Every event too far away, in the time available, for any influence to cross in either direction. Not your past, not your future, elsewhere. And this is the majority of the universe at any moment, by an overwhelming margin. Here is the crucial part. For events in the first two categories, the ones that can actually influence each other, every observer in the universe agrees on which came first. Every single one, without exception, at any speed. Move as fast as you like. You will never see an effect arrive before its cause. But for events in the third category, in elsewhere, observers genuinely disagree about the ordering. One says the supernova came first, another says the earthquake did, a third says they were simultaneous, and all three are right, because the question has no observer-independent answer. That sounds like it should be a catastrophe, and it is not. It is permitted precisely because those events cannot affect each other. The universe is not being careless. It is being exact. It allows disagreement about ordering in exactly and only the cases where the ordering has no consequences, and it enforces universal agreement in exactly and only the cases where something is at stake. Two people, two explanations, one force. Now say it again at the level of the whole universe. Two observers, two sets of clocks, two sets of rulers, two entirely different accounts of when things happened and how far apart they were, and complete, unbreakable agreement about which event caused which. That agreement is what the constant is protecting. It is the boundary between the region where causal order is absolute and the region where it is a matter of opinion. Set the boundary anywhere else, and the two regions shift. Remove it, make it infinite, and the third category vanishes, and the whole structure collapses into that undifferentiated present we walked through a moment ago. There is a quiet consequence of this that deserves a moment, because it resolves something that troubles a great many people about quantum mechanics. Entangled particles produce correlated results across the third category, across elsewhere, and those correlations are real, measured, and confirmed to absurd precision. It looks at first like a violation. It is not, and the reason is exactly the structure we have just built. The correlations cannot be used to send a message, because the statistics each observer sees on their own side are completely unchanged by anything done on the other. Nothing crosses. What is shared is a correlation, not an influence, and correlation carries no ordering. Quantum mechanics and the causal structure of space-time coexist by respecting precisely the same boundary, from opposite directions, which explains something that otherwise looks arbitrary, why the barrier cannot be crossed by pushing harder. People imagine the limit as a wall. You accelerate toward it, you approach it, and at the last moment something stops you, some resistance, some force pushing back, some cosmic hand on your shoulder. That picture is entirely wrong, and the truth is stranger. In this geometry, a change of velocity is not a change of speed in the way you are used to. It is a rotation, not a circular rotation like turning a corner, but a hyperbolic one, a shear in the plane that has time on one axis and space on the other. And what actually adds, when you combine two of them, is not velocity, it is the hyperbolic angle, which physicists call rapidity. Rapidities add perfectly, and without limit. You can go on adding them forever. There is no largest one. But the velocity you get out of a given rapidity climbs more and more slowly as the rapidity grows, and it approaches the invariant speed without ever arriving. Look at the numbers at the Large Hadron Collider. Protons circulating at nearly 7 trillion electron volts are moving at about 0.9999999, one of the invariant speed, 8 nines after the decimal point. The rapidity that corresponds to is about 9.6, not 9.6 million, 9.6. Feed in a great deal more energy, and the rapidity ticks up to 10, 11, 12, calmly, in ordinary size steps, while the velocity adds another 9, and another, and another. The limit is not a wall you hit. It is a place at infinite distance, in the only measure that counts. It is not that you cannot get there because something stops you. It is that there is no there to get to, in the way that no amount of walking brings you to the horizon. So we know what the constant does. It is the maximum rate at which any part of the universe can influence any other part. It is the boundary that keeps causal order from being a matter of taste. It is, to give it the name it should have had all along, the speed of causality. But we still have not answered the question we started with, and I want to be careful not to let it slip past. Knowing what the constant does is not the same as knowing what it is. A speed of causality is still a speed, and the question was, why that number, and what it actually measures? Before we can answer that, there is one loose end to deal with, because if the constant has nothing to do with light, then somebody needs to explain what light is doing, traveling at exactly that speed. Part 11. Why light is on the list at all. The answer is that light has no choice, and it has no choice because it has no mass. In the geometry we have built, mass is not a measure of how much stuff there is. Mass is an impediment to motion through space-time. An object with mass has an internal clock, a rest frame, a point of view. There is always some observer for whom it is sitting still. Getting it to move takes energy, and getting it to move faster takes disproportionately more energy, and the closer it gets to the invariant speed, the more absurd the bill becomes, without limit. That is why nothing with mass ever arrives. Now remove the mass entirely. An object with no mass has no rest frame at all. There is no observer anywhere in the universe for whom it is stationary. It has no internal clock, and with the impediment gone, there is exactly one speed available to it, the invariant speed, in every frame, always. Not a top speed it works up to, the only speed it has ever had, from the instant of its creation to the instant of its absorption. So the rule is stark. If you have mass, you travel below the invariant speed and you can never reach it. If you have no mass, you travel at it and you can never do anything else. There is no third option, no sliding scale, nothing in between. Which means the interesting question is not why light travels at that speed. The interesting question is what else is on the list. The photon is on it, so is the gluon, the particle that carries the strong force inside every atomic nucleus, although gluons are never seen traveling freely because the strong force will not let them out. And so are gravitational waves, which are ripples in the shape of space-time itself, propagating outward from anything massive that accelerates violently enough. Gravitational waves are not made of light. They are not electromagnetic in any sense. They are the geometry of the universe wobbling, and they travel at exactly the speed of light. On the 17th of August, 2017, we watched it happen. In a galaxy called NGC 4993, about 130 million light-years away, two neutron stars had been spiraling toward each other for a very long time. Picture the last seconds. Two objects each more massive than the sun, each about the size of a city, whipping around each other hundreds of times a second, dragging the shape of space into a whirlpool around them. Then they touch and merge, and in that instant, two things leave the scene together. One is a shudder in the geometry itself, a stretching and squeezing of space that propagates outward in every direction. The other is a burst of gamma rays, ordinary light, at the far violent end of the spectrum. They set off at the same moment, side by side. Then they travel. For 130 million years they travel, across a distance the mind cannot hold, through intergalactic space, past clusters and voids, while on a small planet in another galaxy the dinosaurs come and go, and mammals appear, and eventually build detectors. Neither traveller gains on the other in any way that would show. They keep pace across the entire journey. And on the 17th of August, 2017, detectors in Louisiana and Washington, and one in Italy, register the tremor, a stretch and squeeze smaller than a fraction of the width of a proton. 1.7 seconds later, a gamma-ray monitor, in orbit above the Earth, catches the flash. 1.7 seconds. After 130 million years. That gap is a rounding error, on a rounding error, and most of it is explained by the burst, taking a moment to escape the debris of the collision. What it tells us is that the speed of gravitational waves and the speed of light are the same to within roughly 1 part in 1,000 million. Sit with what that means. A phenomenon with no connection whatsoever to electromagnetism. No charges, no fields, no photons anywhere in its description. Travels at what everybody insists on calling the speed of light. Not approximately, not close enough for practical purposes. Identically, to 15 decimal places. That is not a coincidence, and it does not need explaining twice. Both are massless. Massless things move at the invariant speed. The speed belongs to neither of them. And now for the part that should settle the argument permanently. Nobody has ever measured the mass of the photon to be zero. That is not how measurement works. What experiments produce is an upper bound, a statement that if the photon has any mass, it must be smaller than a certain value. The current bound, from studies of the magnetic field carried by the solar wind, and from arguments about magnetic fields on galactic scales, sits at something like 10 to the minus 54 kilograms. That is a fantastically small number, roughly a million times lighter than the lightest neutrino allowed by cosmology. But it is not zero, and it never can be. So consider the possibility. Suppose that tomorrow, an experiment established that the photon has a mass just under the current bound. What would break? Nothing. Not one equation of relativity. The transformation between frames would be untouched, because we derived it from 4 statements about symmetry, with no reference to light at any point. The invariant speed would sit exactly where it sits, with exactly the value it has. The causal structure of spacetime would be entirely unaffected. The only thing that would change is that light would travel very slightly slower than the invariant speed. Its speed would start to depend on its color, with red light lagging a hair behind blue, and we would have to stop calling the constant the speed of light, because light would no longer be traveling at it. That is the whole case, in one sentence. The most famous constant in physics could lose its namesake tomorrow morning, and the physics would not notice. A number that can survive the departure of the thing it was named after was never a fact about that thing. Light is the passenger, not the road. It is worth being honest here about the near misses, because they get misreported constantly. In February of 1987, a star exploded in the Large Magellanic Cloud, about 168,000 light-years away. Detectors in Japan, the United States and Russia caught a burst of neutrinos. 11 events in one, 8 in another, 5 in a third. And the visible brightening of the star was not seen for another 3 hours. Neutrinos beat light by 3 hours, and the headlines wrote themselves. They did not beat light. They left first. Neutrinos stream straight out of a collapsing stellar core almost immediately, while the photons have to fight their way out through the star's overlying layers, which takes hours. The head start was in the departure, not the race. And neutrinos do have mass. That has been settled since the experiments on neutrino oscillation in the late 1990s and early 2000s, which means they travel just below the invariant speed, exactly as the geometry demands. The other episode worth telling honestly is what happened in 2011, because people cite it as evidence of things being hidden, and it is the opposite. A collaboration running an experiment in Italy, catching neutrinos fired 730 kilometers through the Earth from Switzerland, measured them arriving about 60 nanoseconds earlier than they should have, 60 billionths of a second. They checked it for months, could not find the mistake, and then, in September of 2011, published the anomaly openly and asked the rest of the world to tear it apart, which is precisely what a group does when it does not believe its own result, but cannot make it go away. Within a few months the fault was found, a fiber optic connector that had not been fully seated, and a drift in a clock oscillator. The result was withdrawn. Nothing was suppressed, nothing was buried, and the only reason anyone outside the field ever heard about it is that the people who found it insisted on saying so out loud. So the list stands, and light is one entry on it rather than its author. Which brings us back, finally, to the question we have been carrying since the beginning and can no longer put off. If the number is not the speed of light, and not really the speed of anything in particular, then what on earth is it measuring? Part 12. The number we invented. Before we answer it, there is one obstacle in the way, and it is the number itself. 299,792,458. It looks like a measurement. It looks like something the universe handed us, awkward and specific. The way the melting point of lead, or the mass of a proton, looks like something handed to us. And as long as it looks like that, the answer we are heading for will not land, because you cannot accept that a number is a conversion factor while it still smells like a discovery. So consider how we got it. The first person to establish that light takes any time at all was Ole Rømer in 1676, and he did it by watching a moon. Jupiter's satellite Io disappears behind the planet and reappears on a predictable schedule, and Rømer noticed that the schedule slipped. The eclipses ran late when Earth was moving away from Jupiter, and early when Earth was approaching. He presented the conclusion in Paris on the 22nd of November, 1676. Light is not instantaneous, and it takes something like 22 minutes to cross the diameter of Earth's orbit. The modern figure is 16 minutes and 40 seconds. His number was wrong by a third. His conclusion was one of the great results in the history of science, and it came from noticing that a timetable was drifting. James Bradley, in 1729, got closer by a completely different route. He found that the apparent position of every star shifts slightly over the course of a year, because the Earth's own motion tilts the direction from which starlight arrives, the same way rain appears to come at you slantwise when you run through it. From the size of that tilt, he extracted a ratio and got roughly 301,000 kilometers per second. Hippolyte Fizeau brought it down to Earth in 1849, without leaving Paris. He set up a light source at Suresnes and a mirror on Montmartre, 8,633 meters away, and put a spinning toothed wheel in the beam's path. 720 teeth, turning about 12.5 times a second. At the right speed, a flash of light that slipped through one gap came back to find a tooth in the way and vanished. From the speed of the wheel and the distance to the hill, he got about 315,000 kilometers per second. Léon Foucault refined the method with a rotating mirror in 1862 and got 298,000 and, more importantly, showed that light travels more slowly in water than in air. And then, on the 20th of October, 1983, the General Conference on Weights and Measures did something that ought to be far more famous than it is. They stopped measuring it. The meter had been defined, since 1960, in terms of the wavelength of a particular orange line in the spectrum of Krypton 86, and the best measurements of the speed of light were limited not by anyone's apparatus, but by how reproducibly that Krypton line could be pinned down. The uncertainty in the constant was really an uncertainty in the ruler, so the conference inverted the relationship. They declared that the meter is, by definition, the distance light travels in vacuum in 1,299,792,458th of a second. From that day, the constant has an exact value with zero uncertainty, permanently, by decree. It is no longer possible to measure the speed of light. Any experiment that appears to be measuring it is now, by definition, measuring the length of the meter. The most precisely known quantity in physics is precisely known because we stopped asking the universe and started asking a committee. That should tell you something. You cannot do that with a real physical property. Nobody can decree the mass of the electron or the strength of the strong force. Those numbers push back. This one did not, because there was nothing on the other side of it to push. And there is a second clue, stronger than the first. Across whole fields of physics, people simply set the constant to 1, not approximately 1, exactly 1, as a choice of units, the way you might choose to measure distance in light years and time in years, so that light travels 1 unit per unit. Do that, and the constant vanishes from every equation in physics. All of them. The relation between energy and mass becomes energy equals mass. The space-time interval loses its coefficient. Not one prediction changes. Not one result is lost. Nothing becomes ambiguous. Ask yourself what kind of quantity can be deleted from every equation in a subject by a change of bookkeeping, without any consequence at all. The answer is the kind that was never describing a property of the world in the first place. It was describing a relationship between 2 units we invented. This is also the honest answer to a claim that circulates persistently, that the speed of light has been decaying over time, that it was far faster in the distant past, and that light from objects billions of light-years away could therefore have reached a much younger universe. The best-known version of this argument assembles the historical measurements we just walked through, from Roma onward, and points out that they trend downward. And they do trend downward, for a reason that has nothing to do with physics. Every one of those historical values is consistent with the modern one within its own stated error bars, and the scatter shrinks steadily as the instruments improve. What is decaying is the uncertainty, not the constant. But there is a deeper reason the claim cannot be assessed as stated, and it is the point we just established. Since 1983, the constant is a definition, so asking whether it has changed is like asking whether the number of centimeters in an inch has changed. The question that actually has content is whether the dimensionless combinations change. Above all, the fine structure constant, that famous 1/137, which is built out of the charge on the electron, the constants of the vacuum, and the invariant speed together. Because it is a pure number with no units attached, it means the same thing to any observer using any measuring system anywhere. And we can check it. In Gabon, at a place called Oklo, a body of uranium ore went critical on its own about 2,000 million years ago, and ran as a natural nuclear reactor for a very long time. The isotopes it left behind are exquisitely sensitive to the value of the fine structure constant at the time, and they constrain any drift over those 2,000 million years to a few parts in 100 million. There are also claims, from quasar absorption spectra, of a very slight variation across the sky at around the 4 sigma level, and they remain unconfirmed and are widely suspected to be an instrumental effect rather than a real one. There is also a serious research program, not fringe at all, exploring cosmologies in which the invariant speed was much higher in the earliest moments of the universe, proposed in the early 1990s and developed at the end of that decade as an alternative to cosmic inflation. It is a respectable idea with a real motivation. It has simply not matched the observations as economically as its rival, and defining it precisely turns out to be much harder than it sounds, for exactly the reason we have just been discussing. So the number is ours. It is large and awkward because we evolved at walking pace and invented one unit for how far and a completely separate unit for how long, never suspecting the two might be the same kind of thing, which means we are finally out of obstacles. There is nothing left standing between us and the answer. Part 13. What the constant actually is. It is an exchange rate. That is the answer, and it is worth saying as plainly as possible before we dress it up. The number is the conversion factor between the units human beings invented for measuring distance and the units human beings invented for measuring duration. 1 second is 299,792,458 meters, not equivalent to, not corresponds to, is, in exactly the way that 1 inch is 2.54 centimeters. Read that again, because everything in this video has been building toward it, and it goes past very quickly. A second is a length, a meter is a duration. They are measurements along the same object, taken in two different directions, and the only reason we use different words and different units for them is that our ancestors could not perceive the connection. Why could they not perceive it? Because of the size of the exchange rate compared to us. A human being sprinting flat out covers about 10 meters in a second. In the units the universe actually uses, that second is nearly 300 million meters long, which means every motion any creature on this planet has ever performed has been overwhelmingly a motion through the time direction, with the barest sliver of it turned sideways into space. We were never going to notice that the two were the same. It would be like a species that could only ever move a millimeter north, trying to work out that north and east are both directions. So the invariant speed does not tell you how fast anything goes. It tells you how much space a given amount of time is worth. It is the ratio that lets you write down a single geometry containing both, instead of two separate stages with events awkwardly shuffled between them. That is the metrological way of saying it. Here is the geometric way. The constant is the one free parameter in the symmetry of space-time, the single number left undetermined when you demand that space be uniform, have no favorite direction, play no favorites among steady velocities, and permit consistent translation between points of view. It is the coefficient sitting in front of the time term in the invariant interval, the thing that makes the subtraction possible. It sets the slope of the boundary between what can influence what. And here is the causal way. The constant is the maximum rate at which any part of the universe can affect any other part. It is what guarantees that every pair of events capable of influencing each other is ordered identically for every observer who will ever exist, while permitting disagreement precisely and only where the disagreement can do no harm. It is the reason this caused that is a fact about the world rather than an opinion about it. Those three answers are not competitors. They are the same statement seen from three sides. The same way a mountain looks like three different mountains from three different valleys. The exchange rate between space and time is what fixes the geometry. The geometry is what fixes the causal structure. The causal structure is what makes events orderable. One number, doing all of it. This is also why the constant kept turning up in places it had no business being, back at the very start. Go back to that stationary object on the table, the coin, the stone, the paperweight, and the equation that says its rest energy is its mass multiplied by the constant squared. There is no light in that situation, and there never was. What the equation is actually saying is that energy and mass are the same quantity measured in different units, and the constant appears because the units of energy involve time, and the units of mass do not, and something has to convert between them. Squared, because the conversion has to happen twice over. It is the same exchange rate at work, doing exactly the same job it does everywhere else. Every appearance of that constant in an equation with no light in it is a place where somebody had to translate between a duration and a distance, which is to say, almost everywhere. Which brings us to light, and to the sentence this whole thing was built to earn. The speed of light is not about light. The constant does not belong to the photon, was not set by the photon, and would be exactly what it is in a universe with no photons in it at all. We derived every part of it, the transformation, the invariant speed, the causal structure, the impossibility of crossing the boundary, from four statements about the uniformity and consistency of space and time, with light mentioned nowhere. Then, at the very end, we asked what would happen to be traveling at that speed, and the answer was anything without mass, because things without mass have no rest frame, and therefore no alternative. Photons qualify. So do gravitational waves, which are not made of light, and travel at the identical speed. And if the photon turned out tomorrow to have a mass just under the current experimental bound, it would drop off the list, travel a fraction slower, and nothing in the structure would so much as flinch. Light is the passenger, not the road. It has been riding on something it did not build, and because it was the first thing we could measure, going fast enough to notice, it got its name on the sign. It is worth noticing how thoroughly this dissolves the puzzle we started with, the one about the universe seeming to conspire. There is no conspiracy, because there is nothing to arrange. Nobody is holding photons at a particular speed. Nobody is preventing rockets from exceeding it. The geometry has one exchange rate built into it, and everything that happens is already happening inside that geometry. The way every triangle drawn on a flat sheet of paper already has angles summing to 180 degrees, without anything enforcing it. Enforcement is the wrong picture entirely. There is no rule and no rule keeper. There is a shape, and the shape is what having a universe consists of. There is a final turn of the screw here that is worth sitting with, and it comes from Eugene Wigner in 1939. Wigner asked what a fundamental particle actually is, mathematically, and gave an answer that is now the standard one. A particle is a representation of the symmetry of space-time, not an object that happens to live inside space-time and obey its rules. A pattern in that symmetry, labeled by exactly two numbers, how it behaves under boosts, which we call mass, and how it behaves under rotations, which we call spin. Follow what that means. The symmetry group we spent this video building out of 4 innocent assumptions is not a set of rules imposed on particles from outside. It is what particles are made of. The invariant speed is not a restriction on matter. It is inside the definition of matter. There is no version of an electron that could exist without it, because there would be nothing left to be an electron. So the standard framing does not merely have the emphasis wrong, it has the direction of the whole relationship reversed. The universe does not conspire to keep photons at a fixed speed and to hold everything else below it. There is a geometry, with one number in it, and that geometry is what mass and spin and cause and effect and distance and duration all are. Light obeys it, in the only way something without mass can, which is completely and without exception, and it has been carrying the credit ever since. The number itself, the 299 million and change, records nothing about the universe. It records the width of a human stride, and the length of a human day, and the fact that we invented our rulers and our clocks before we understood that they were measuring the same thing. And yet, having said all of that, having derived the structure from nothing, having stripped the light off the constant, having found out what it actually measures, there is one question left, and it is the one nobody can answer. The 4 assumptions told us that there must be such a constant, and that everyone must agree on it. They could not tell us what it is. That dial was left unset, and something set it. Part 14. The number nobody can explain. The structure explains itself, and the number does not. That is the residue of the whole argument, and it is worth holding carefully, because it is easy to miss underneath the satisfaction of having found an answer. 4 assumptions, mild enough that denying any one of them would make science itself impossible, forced a transformation with exactly one free parameter. 2 of the 3 possible values for that parameter produced universes with no cause and effect, or no matter, no magnetism, no distance, and no events. The 3rd produced this one. Every part of that is derivable, and none of it required light. But the value was never derivable, and it still is not. There is no argument from symmetry, or from consistency, or from anything else anyone has found, that says the exchange rate between a second and a meter should be 299 million and change, rather than 1,000 times more or 1,000,000 times less. The mathematics is perfectly happy with any positive value. It cares enormously about the sign, and not at all about the size. Now, the obvious response is the one we have already met. In natural units, the number disappears, so there is nothing to explain. Set the constant to 1, and the question dissolves. And that is genuinely an insight, not a dodge. It is the clearest demonstration that the number is a unit convention rather than a physical parameter. But be honest about what it does. Setting the constant to 1 does not tell you why a human second is worth that many human meters. It moves the arbitrariness out of the equation and into the definition of the units, where it is less conspicuous. The strangeness has not been removed, it has been rehoused. It is worth being precise about how unusual this situation is, because physics has two very different kinds of unanswered question, and they get confused constantly. There are questions we cannot answer yet. What dark matter is made of, how gravity behaves at the smallest scales, why there is more matter than antimatter. Those are gaps in a map, and there is every reason to expect somebody will eventually fill them in. Then there are questions where the theory that works perfectly also tells you, structurally, that it has nothing to say. This is one of those. The derivation does not fail to determine the value through some weakness we might one day repair. It determines everything else completely and hands the value over untouched, as though it were never its business. A theory that confident about the architecture and that silent about one number is telling you something, and nobody has worked out what. There is also a related question that is genuinely open and worth flagging, which is whether the four assumptions are exactly true or only very nearly so. Several serious approaches to combining gravity with quantum mechanics allow for the possibility that the symmetry we have been leaning on is not fundamental but emergent, something that holds beautifully at every scale we can reach and breaks down at energies far beyond them. If that were so, the invariant speed might turn out to depend very slightly on energy, and photons of wildly different colors, emitted at the same instant, would drift apart over a long enough journey. People have looked. Gamma-ray bursts billions of light-years away have delivered photons differing in energy by a factor of millions, arriving within about a second of each other, and no drift has ever been seen. The symmetry holds, so far, everywhere anyone has been able to point an instrument. And underneath the question about the value, there is a stranger one about the sign, and it is the one that stays with me. We eliminated the two rejected cases on the grounds that they produce universes in which nothing can happen, rotate time into space, and cause and effect stop meaning anything. Set the exchange rate to infinity, and there is no matter, no separation, nothing to be an event. Only the third case yields a world in which things occur in an order. There are two ways to read that, and they point in opposite directions. The first reading is that we are simply looking at the only kind of universe capable of containing something that could look. The geometry is what it is. The other options were never live possibilities in any meaningful sense, and the fact that this one permits observers is not an explanation of anything. It is a condition of the question being asked at all. The second reading is more unsettling, and, on some days, more persuasive. It is that causality might be the deeper thing, and the geometry of space-time might be downstream of it. That the shape of the universe is whatever shape it has to be in order for effects to be able to follow causes, and the finite exchange rate between space and time is the price of admission for a world in which anything can be said to lead to anything else. Nobody knows which of those is right. It is possible that the question is not the kind of question that has an answer, and it is possible that somebody will find one in the next century and it will look obvious afterwards, the way most things do. What we can say is smaller and more solid than either. The number in the textbook is not a fact about light. It never was. It is the rate at which the universe converts duration into distance, and light travels at it for the same unremarkable reason a leaf travels at the speed of the river, because it has nothing of its own to hold it back. There was one dial, and it had to be set. The universe set it, and left no note explaining why. So the next time you hear that nothing can travel faster than light, you might let the sentence sit for a moment before it goes past. It is true, and it is one of the least interesting true things about the situation. The photon is not the boundary. It is the most conspicuous thing riding along it. The first traveler we happen to catch moving at the speed the universe uses to keep its own accounts. And the accounts are being kept right now, everywhere, in the wall behind you, and the light in your window, and the ground under the building, at the rate of 299,792,458 meters for every second that passes. It has been doing that since long before there was anyone to name it, and it will go on doing it long after. We simply gave the credit to the wrong traveler, and it has taken a very long time to notice.